Eigenvalues and eigenvectors. These are defined for square matrices like determinants. A is an m by m matrix. An eigenvector of A is a non-zero vector x such that Ax equals lambda x for some scalar lambda. In this case, the scalar lambda is an eigenvalue and x is the corresponding eigenvector. We'll try to get a better understanding of these new terms by solving some examples. Is this vector an eigenvector of the matrix? What is the eigenvalue? Okay. For this vector to be an eigenvector of the matrix, this should satisfy this kind of equation, Ax equals lambda x. Okay, so we try to get the product. The matrix is now 5, 2, 3, 6, and the vector is -1 and 1. Okay, row, column, that is -3. Second row, column, that is 3, right? -3 plus 6. Okay, so we have to write this one in the shape here, lambda and x. X is -1 and 1 right now, this x, okay? And to be the same, we have to put here 3. So 3 is the corresponding eigenvalue. And also, this vector is an eigenvector of the matrix, okay? A is given in this matrix, and we will show that 7 is an eigenvalue of A, and we'll find the corresponding eigenvectors. Okay, that is in plural form. We'll see why we have that. Okay, now once 7 is an eigenvalue, then we can write in this way, Ax equal 7x for some non-zero vector. Okay, now from this one, A x minus 7x must be 0, and we can write this one again, A minus 7 identity, and x equal 0. So this matrix should have non-trivial solution. This is a homogeneous equation. Now it should have non-trivial solutions because x is non-zero. Okay, let's try to organize this matrix. A is 1, 6, 5, 2, and minus 7 identity 1, 0, 0, 1. So along, after multiplication, along diagonal, the values 7 and 0, so that here we'll try to subtract minus 7, so it's minus 6 and 6, and minus 7, so that 5 and minus 5, right? Okay, so we have to solve the problem here, x equals 0, and once we can find non-trivial solution, that will be corresponding eigenvector, right? Okay, now for this one, we may start with augmented matrix, minus x, 6, 5, minus 5, and right side 0 vector. Okay, scaling makes 1, minus 1, 0. Again, scaling 1, minus 1, 0. The same. So with a replacement, we can make 0, 0, 0 here now. So we have basic variable, x1, and x2 is a free variable. So first row is saying x1 minus x2 equals 0, which is same as x2. x2 is free, so that we have here x2. From here, now x, the left-hand side, is same as x2, the free variable, and 1 and 1 direction. So for every non-zero choice of x2, it will become the solution of this homogeneous system, and it will be an eigenvector, so that there are infinitely many eigenvectors for the eigenvalue 7. So that's the reason we are using here Fourier form. Okay, now for example, if we choose x2 equal 1, then x becomes here 1 and 1. Okay, from here, now a times x, that is, a is 1, 6, 5, 2, and now that is 1 and 1. That is now 7, 1 plus 6, 5 plus 2, again 7. So that can be written here 7 times 1 and 1. Right? So here ax equal 7x. So 1, 1 is an eigenvalue, and the corresponding eigenvector and corresponding eigenvalue is 7. Now, for example, we choose x2 equal minus 2. Then x must be minus 2 and minus 2. From here, now ax equal the same metric, 1, 6, 5, 2. X is now minus 2 and minus 2. So that here that is, okay, minus 2, minus 12, minus 14, and minus 10, minus 4, again minus 14. So that is same as 7 times minus 2, minus 2. We have here ax equal 7x. So for various choices of x2, they are all eigenvectors for the eigenvalue 7. Okay. Now, lambda is an eigenvalue of a. That means that ax equal lambda x for x non-zero, right? Then here, the homogeneous system. So from here we can get this system should have non-trivial solution. That means has at least one free variable, because x is non-zero, and also the determinant of lambda I must be 0. Okay, so that determinant is 0, so that we can have non-trivial solution. So this one will be used when we try to find eigenvalues and then eigenvectors. Okay. Now we'll add one more line to the invertible metric theorem. A square metric A is invertible. It's the same as here the homogeneous system has the only trivial solution. Now that is the same as this one. The number 0 is not an eigenvalue of A. Now we'll consider the lambda. We assume lambda is 0, an eigenvalue of A is 0. Then, so we'll try to show that once it is 0, then A is not invertible. Okay. Then ax, there are some non-zero x such that ax must be 0 Okay, this is eigenvalue 0 and x. That will be 0. So the homogeneous system has a non-trivial solution which contradicts to this fact. So in this case, A is not invertible, right? So the other direction also can be proved quite easily, and so that they are the same. Once A is invertible, then 0 cannot be an eigenvalue of A. Okay, here we have subsection characteristic equation. The scalar equation determinant of A minus lambda I equals 0 is called the characteristic equation of A, and the polynomial that itself determinant of A minus lambda I, so we are using the notation P lambda, is called the characteristic polynomial of A. The solutions of the characteristic equation determinant of A minus lambda I equals 0 are eigenvalues of A. That means that to find the eigenvalues of A, we have to solve this equation, characteristic equation. Now let's try to find the characteristic polynomial eigenvalues and corresponding eigenvectors of the matrix. Okay, let's begin with A minus lambda I. That's A is A2, 3, 3. Lambda I minus lambda I is 1, 0, 0, 1. So here we can get the matrix, and along the diagonal we subtract lambda. So there's 8 minus lambda, and that is 2, and 3 minus lambda. Okay, so its determinant is just AD minus BC, 8 minus lambda, and 3 minus lambda, and minus 6. Okay, so here that is lambda squared minus 11 lambda and plus 24 minus 6. So we have lambda squared minus 11 lambda, and that is plus 18 equals 0 is the characteristic equation, and this portion is the characteristic polynomial. Now we have to solve this equation to get eigenvalues. Okay, now 18 can be separated into 2 and 9, and if we put here minus minus, then also this one is lambda separation. So from here we have 2 eigenvalues, that is 2 and 9, right? Okay, from here, now once lambda equal 2, for each case we have to find eigenvectors. Okay, lambda is 2, then A minus lambda I, we subtract 2 along the diagonal. That is now 6 and 2, and now 3 and 1, right? So we have to solve A minus lambda I x equal 0, right? We have to solve that. Okay, so this homogeneous system must be solved. How? We can start with the augmented matrix and then apply elementary row operations. 6, 2, 0, 3, 1, 0. Okay, two rows are essentially same. After scaling, you can get that one. So here, from this one, we can reach at now, okay, that is Okay, again scaling 1, 1 over 3, 0, and using replacement we have 0, 0, 0, right? So x2 is a free variable, and x1 equal minus 1/3 of x2, and x2 is x2. So from here, x can be obtained with x2, and direction is minus 1/3 and 1. We may rewrite this one in this way, and using integer values, again x2, because it is arbitrary, we are using again x2, and after multiplication of 3, we have minus 1 and 3. Right? Okay. So scalar multiple of this vector will be the corresponding eigenvectors of the eigenvalue 2, right? And how about lambda is 9? Okay, then here a minus 9i, and 9 will be subtracted along the diagonal. Then there's minus 1 and 2. Okay, 9 is subtracted here. Minus 1, 2. 9 is subtracted 3 and minus x. Okay, 3 and minus x. Okay, that metric times x must be 0, right? We have to find the x. Now, again, same way, by using the augmented metric, we can get it. Here, the augmented metric is minus 1, 2, 0, 3, minus x, 0. Here, essentially, these two rows are the same. You can eliminate these two values through replacement. Okay, so that we have here now 1, minus 2, 0, 0, 0, 0. That means here x1 is 2x2, x2 is x2, so that we can get here now that is x2, and then here 2 and 1. So we can conclude in this way. Now, these are eigenvectors for the eigenvalue 9. Okay. Okay. Find the characteristic polynomial and all eigenvalues of the metric. Okay. Now you can get quite easily. But now start with a computer program in MathTalent, and here we define A, the same metric, and we are using characteristic polynomial A, and output will be with x variable. So that's this one, and we solve the polynomial equals 0, and we get eigenvalues. That is here minus 2, 2, and 3. That means this can be now factored in linear terms. That is x plus 2 and x minus 2. Not lambda x. We are using lambda notation. And then now x, okay, minus 3. Right? Okay. Now, by using EIG command, built-in command, we can get here the collection of eigenvectors and diagonal metric of eigenvalues. So here these are eigenvectors, and the corresponding eigenvalues are 3, minus 2, 2. Okay, and once we get that way, then the metric P times the diagonal metric and inverse of P will produce the original metric. So see if it is making the given metric is exactly the same as that one. Okay. Now Okay. Okay. Now, matrix similarity and the diagonalization theorem will continue in the second part. Thank you.